Alright, so we're taking a look at some solutions to the section 2.4 worksheet. And actually, as I was getting ready to do this, I see a typo that I didn't see in class. This is actually homework problem number 5, or exercise number 5 in section 2.4. And so let me grab a red pencil here. So this should be pi fourths, comma 3. Okay, I misread the problem in the textbook. Okay, so this is number 5 in 2.1 or 2.4. Good. Okay, so now this is going to make a little bit more sense, but let's just rewrite this, and let's just say that this is at the point. I think I was working with some students in class. Well, let's just say this is at the point x equals pi, and let's go ahead and construct the equation of the tangent line. Good. Because what I wanted to get to was the more general case. So people were having questions about just how do you get the equation of the tangent line. So suppose I have a function y equals f of x at x equals a, and we want the tangent line. Okay, so the point, we need a point and a slope, right? So the point that the line goes through, you plug in x equals a, and then the a goes into the f, so that's f of a. Okay, and so this is the point that the line should go through. So graphically, right, if you're sitting here at the point A, right, your tangent line should look like that. And so the point that the line goes through would be a comma f of a, and then the slope of the line is f prime of a. Okay, so f prime of a. Good. Now for us, we have y equals 3 tangent of x, and then we're taking a look at things at x equals pi. Okay, so at x equals pi over here, let's see, I guess that's going to be 0, isn't it? The tangent of pi is 0. So if we plug in, if we want to use the point pi, the point that we would be going through is actually pi 0, right? Notice that was an error in the notes, because we wanted it said in the question that we wanted to go through the point pi 4/3, but you see this was the error here. And so if we want to choose pi for our value, then the line will have to go through pi 0. Okay. So then to get our slope, we just take the derivative, 3 times secant squared pi. And now to compute that, right, the secant of pi is -1, so we can get that off the unit circle. So that's 3 times -1 squared, which would be 3. Good. And so in this case, we would have y minus 0 equals 3 times x minus pi. Good. So that would be the equation of our line. Yeah, sorry about that error with the point. I didn't read the problem correctly when I was writing it down. Good. All right. So let's take a look at the other questions. I don't want the video to go too long, but let's just take a quick look at the number 3. So you'll notice that I'm giving you a function of time, right? And I'm asking, we're told that this is a displacement function. And so the derivative is going to be the velocity, and the second derivative is the acceleration. So here we're going to have to compute h prime of t, and then plug in 2. And then here we're going to need to take the second derivative and then plug in 2. Okay, good. So let's try that out. So our h of t, whoops, h of t, let's try that again. We're still running, is 3 plus 2 cosine of t divided by 1.2 to the t power. So h prime of t. The derivative of 3 is 0, so that's not going to do anything. And then here we're going to have a product, or a well, I guess we're going to need to do the quotient rule for that, aren't we? So we're going to have the derivative of the top, which is minus 2 sine of t, times the bottom, 1.2 to the t, minus the top, 2 times cosine of t, times the derivative of the bottom, 1.2 to the t, natural log of 1.2, all divided by the bottom function squared. Good. Now in order to evaluate this, we have to evaluate it on our calculator. Okay, I think I will pause to do that. All right, so if we compute this, I plug this into my calculator and I get minus 1.157 53 ... Okay. By the way, remember to be in radian mode. We use radian mode because the formula for the derivatives are actually going to be different if we use degrees. Okay, so be sure you're in radian mode. Okay, let's take the second derivative now. Second derivative with respect to t. Now, it might be easiest just to factor this 1.2 out, so maybe I'll simplify h prime first. Right, because if I factor in 1.2 to the t out of the top, then I'm left with minus 2 sine of t, minus 2 times the natural log of 2 times the cosine of t, and then that's all over 1.2 t to the t squared. And notice that one of these cancels with one of those, so that cancels with one of those. Right? And so now I just have, to simplify my derivative before I actually compute it, I get minus 2 sine of t minus 2 natural log of 2, this is just a constant, times cosine of t, all divided by 1.2 to the t. Good. Now when I differentiate this is going to be a little bit of a mess, but not too bad. Right, because it's the derivative of the top, so that's going to be minus 2 cosine of t. Then the constant part just carries along for the ride, times the cosine of t, so that's going to be sine of t if I differentiate. Good, and then I just bring up the top function, minus the top, and here I'm just copying down the numerator, and then that's going to be times 1.2 to the t, natural log of 2. Right, and then it's all divided by 1.2 to the t squared. So that's a big mess. But yeah, we could just plug in 2 now to get that. And hang on again, I'll go get my calculator. Okay, so I get that the second derivative, way down here at the bottom, is 1.0193 ... Well, let's rounded it off. Okay, that's good. So just to check units, if my h of t is in feet and time is in seconds, then h prime of t is in feet per second, and the acceleration then, down here at the bottom, the units are feet per second squared, or feet per second per second. Good. Oh, that's kind of a mess. All right, so that gets us through the front page.